All right, take it away, Kahlil.
Thank you. Uh, Hello, everyone. My name is Kahlil Dixon, and I'm going to talk to you about optomechanical entanglement generation. So, uh, quick overview of what I'm going to speak on today. I'm going to give a little introduction and go over some previous work in optomechanical entanglement. And then essentially I'm going to discuss a paper that we have currently under review about room temperature generation of this form of entanglement, and then what we're currently looking at, which is entanglement output when you have squeezed light input into an optomechanical cavity. So just one sec. Okay. You all can still see the presentation, right?
Yes.
Okay. Okay. So recently there was an effort at LIGO to reduce noise due to radiation pressure effects. The quantum aspect of this noise was a significant challenge to address. So in order to do this, Dr. Corbett's group created a tabletop scale platform for testing and prototyping the quantum radiation pressure noise evasion techniques before they were to be implemented in LIGO. His group knew from their previous research that the radiation pressure noise could be increased relative to the cavity circulating power by installing a movable micromirror into their optical cavity. These mirrors have a diameter about a width of a hair, a mass of about 50 nanograms, and there's an image of them on the slide. I think they're the small dots in the rows in this small device that's being held here. They ultimately found that the quantum radiation pressure effects were dominant in this tabletop system, even at room temperature. This work helped expedite work on the quantum radiation pressure evasion, which led to the paper that reignited Dr. Corbett's group's interest in optomechanical entanglement experimentation. They found these cavities, optomechanical cavities, can demonstrate squeezing at room temperature as well. And our work currently under review is a cautious next step using models and data from previous experiments. We are able to predict optomechanical entanglement from relatively the same optical setup as that used in the squeezing paper, around the same frequency range as the squeezing results displayed in the bottom right here. Let's see. So previously it was thought that the optomechanical cavities could produce entanglement, but our study is the first to consider noises, loss, temperature, and other experimental complications. This is possible thanks to work by with Corbett, Mavalava, and others. This year, a few groups have even achieved optomechanical entanglement experimentally. Chen, Rossi, Mason, and Schleiser demonstrated narrow band bipartite optomechanical entanglement of two optical fields experimentally using a optomechanical cavity cooled to 4 Kelvin. So our work shows or argues that or predicts that this same effect can be seen in a cantilever micromirror type optomechanical cavity at room temperature and below. On the left is an experimental configuration we considered for the simulations, and our code each necessary optical element. is included to match the experimental data and better model realistic losses. On the right is a table of parameters used in the simulations in the paper. So they allow a stable optical spring while yielding non-zero entanglement. And our model assumes double homodine measurement of the sideband quadratures. So, and we use these measurements to arrange the covariance matrix from which we can calculate the entanglement. Let's see. Yeah. So to quantify the entanglement, we use the logarithmic negativity measure. It allows for fast computation of the output entanglement. This measure is normalization dependent. So to be sure we were using the right form of the variance matrix and the right normalization, we double checked with a separate entanglement measure, one that I call Duan's measure of inseparability, which relies on equations as well, but a good amount of them. So yeah, and my implementation of this, the Duan measure is the blue curve and the logarithmic negativity is the red. And my implementation of this fails at high frequency, but it is independent of normalization, and it shows that our choice of normalization and form of EN was the correct choice for our data. Let's see, so the results from our paper show that weak output entanglement can be expected at room temperature and below. The top right shows that the losses also play a major role in the output entanglement for these parameters. And then the bottom right plot confirms the hypothesis that the entanglement output is related to the ratio of noises in this system, where quantum noise is dominant if and only if entanglement is relatively strong. And then the bottom left was just to show, one, that cooling below 4 Kelvin is not beneficial to this method of entanglement generation. And two, if we could adjust our cavity length, the benefit maxes out at 1 millimeter cavity lengths, and below that it's flat. You get no more increase in entanglement generation expected. So yeah, our current work all stems from John's idea on inputting squeeze light into the optomechanical cavity. Some analytical motivation for this comes from the fact that when the quantum noise is dominant in the cavity, the squeezing of the single input field is strongest. So by hand calculation shows that under the optomechanical interaction Hamiltonian, the linear approximation of that Hamiltonian, the squeezing is doubled or enhanced, thus hinting at a enhanced optomechanical entanglement effect as well. So currently we are working on looking at entanglement outputs from these input squeezed, these different input squeeze cases. But before we get into that, we quickly note that our parameters for this part of our work have shifted due to some numerical instabilities in the previous parameter space. We use one that is a rough projection of the parameters used in the experimental paper that I discussed earlier. And the main difference between the two is that for our paper, we found that you could see entanglement, but only if you were very certain of your double of your double homodine measure, you had to have very little uncertainty in your actual measurement, versus theirs, they had like about an order of magnitude higher noise could be allowed for them to still see their entanglement, uh, just for the different parameter spaces. So the results of this are shown in the right plot. Under these parameters, the unsqueezed input yields a maximum logarithmic negativity of about 0.3. The plot on the right considers the case of two one-mode squeezed coherent states entering the optomechanical cavity at the same squeezing strength of about R equals 1.7. With each their own independent squeezing angles, we plot one angle on the X and Y, and we see it, well, here at this squeezing strength, a maximum of about 0.8. But we notice that we see higher output entanglement, or we can predict higher output entanglement from inputting squeeze light, but we also can see inputting squeeze light can lower entanglement below what we were seeing for coherent light, unsqueezed coherent light. So next is just a plot just to show that the entanglement you get from squeezing both coherent states maxes out at 2. The benefit you get to squeezing both coherent states max out at about R equals 2. This plot was done at one of the maximum points of the previous plot. So, you don't need to squeeze past R equals 2, thank God, to get this enhanced entanglement output effect. So next thing I looked at briefly was rotating the squeezing angle to try to get it to a frequency where it's similar to the frequency of the mechanical oscillator. And that actually yields very little benefit. It's surprising that it yields some benefit at all. So what happens here is that it plateaus at squeezing of above 4 for each arm or for each input state. But it's overall not more effective than just non-rotated squeezing angle, non-frequency dependent rotating squeezing angle inputs. The maximum entanglement you get from this is about 1.08, which is only slightly higher. So next we looked at the 2-mode squeezed input. And here we initially thought we had 0 output entanglement, but that's not quite the case. So we have about the same maximum as the 1-mode squeezed case for entanglement, but lower minimum output entanglement of we have very, very low output entanglement at the low points for strong squeezing in between these arches. So with these results, we were kind of hoping there would be regions where the optomechanical cavity would act as a disentangler, and we're still working to investigate that as part of our future work. So currently right now we're investigating these current results, and we're gonna look at the enhanced squeezing with our simulation. And then from there, we will actually extrapolate a little bit to multiple resonators. We're currently working on some single photon simulations to try to see this disentangling effect for few photon states with this would be without the same loss and thermal noise considerations that we had before, but it would help to quantify what's happening in the previous plot, and then we're going to be looking at state and process tomography to investigate the idea of the disentangler and detangling effects of the cavity, and then so on from there. That's all I have for now.
All right, thanks for your talk. Are there any questions for Kahlil? If you have a question, just use the raise hand feature. So I have some questions. If you go 2 slides back.
Yeah.
So it looks like the maximum value of the entanglement is 1. Is that correct?
It's about 1. Yeah.
So, that's roughly 1 like EBIT, or 1 like amount of entanglement that's equivalent to 1 Bell state. And since you have these infinite degrees of freedom, you might hope for more entanglement. And so, I don't know, is it possible to try to increase the amount of entanglement present in the experiment?
That's what we were trying to do with inputting the squeezed light. So, I mean, we started with outputs of about, for this space, 0.3 at any individual frequency. But I'm not entirely, so yeah, we are looking to increase the output entanglement. I'm not entirely sure how to really get that. So we're going to look at other input cases, but yeah. So we want to see increase. I want to see an increase in entanglement from some of the scenarios we're looking at. But,
yeah, I mean, it might simply be impossible. Like maybe an analytic calculation you could do is for some of the experimental parameters fixed analytically. Sometimes you can take the limit as the squeezing strength goes to infinity, and that might give you an indication that it's simply impossible in the experiment to get much more than this, given the fixed parameters. But if you tune the experimental parameters a bit, maybe you can get more out.
yeah. I will look at that. Taking some limiting cases. Yeah, I mean, so for the most part, if you take any of the squeezing to infinity, it kills the entanglement.
Really?
Yeah. So for not only, so here, as you increase your squeezing strength, you get less and less, angles that give you non-zero output entanglement. So the blue regions are very low output entanglement. And then
with the 2-mode squeeze vacuum state, like the ideal 2-mode squeeze vacuum, as you take the squeezing strength to infinity, the entanglement actually goes to infinity. So
you're right.
it has to be something with the noise parameters. It just doesn't allow you to. I think you were about to say something else. I interrupted.
No, it's fine. Yeah, I assume it's something about the noise or dampening in the system that's really cutting into or really taking away from the input entanglement. But so for the, for a 1-mode squeeze, the maximum is they can take, I guess, is about squeezing strengths of 2 in each input. So any beyond that, it decreases to about 0.3 is the minimum, as though it wasn't squeezed, as though they weren't squeezed at all. If you go higher and higher, in your squeezing strength, and then the rotated case, it maxes out, so it plateaus at about 1. So yeah, I'm looking for some cases where it would increase a little bit more with higher input squeezing, but it may be due to some of the losses and noise effects and things like that in our system.
Okay. I have another question, actually. So you were talking about logarithmic negativity and Dwan's measure of inseparability. Can you go back to that slide? You had the plot, you were showing like Q over T.
Yeah.
Yeah, that's the one. So you said that you wanted to make sure the normalization was correct. And then we look at the plot, and should we expect these curves to agree, like overlap precisely, or just follow each other qualitatively like we see?
Just the qualitative sense. Yeah, just in the qualitative sense. The Dwan measure, I think, stays between 0 and 1 for when you have entanglement, or something like R is between 0 and 1. But so this is essentially just a plot of them, and they just happen to be near each other. So they're not supposed to match up per se. It's just in the slope, and they should follow the same trend.
Okay. All right. Thank you. Are there other questions? I'll ask one more since we have a little time. Are there other entanglement measures that you considered? I mean, log negativity is a very nice one, and it has certain operational meanings. And it's, as you said, easy to compute. But is there any other one you might consider?
We haven't considered any others, but I think we're open to using other measures, like especially any that can simplify the overall experiment. If we don't have to do I think we have to, but if we don't have to do the double homodine measurement, let's see. Yeah, if we don't have to have the double homodine set up, that would be great.
Okay.
But yeah.
Okay, so thanks for the talk. We can go ahead and have a break. We'll have an extra